Imagine you're walking through a dense, lush forest. Each step you take feels deliberate. You plant your foot, and only then does the next moment of your journey begin to unfold. One step, then a second, and then a third. Time itself seems to guide your movement, with each moment dividing into what has been and what is now, leaving a trace of memory behind you. This act of stepping, of creating the path moment by moment, isn't about discovering a pre existing trail, but about crafting it as you go, with each step a numerical construction emerging from the flow of time and the workings of your mind. This experience of time, this process of creating each step moment by moment, forms the cornerstone of Intuitionism, a philosophy of mathematics championed by Dutch mathematician L.E.J. Brouwer in the early 20th century, who regarded Intuitionism as the foundation of all of mathematics. For Brouwer, mathematics isn't about discovering truths that are already out there, it's about building those truths, step by step, in the mind. Brouwer saw mathematics as originating from our experience of time. Just as one moment flows into the next, leaving the previous one in memory, numbers arise in a similar way as a mental construction, starting with 1, then moving to 2, then 3, and so on, each number emerging as we generate it. This process, which Brouwer called tuity, forms the basis of the first principle of Intuitionism, or rather, the first act of Intuitionism, as Brouwer called it. Mathematics, he argued, is a languageless activity rooted in this primal perception of time. The sequence of natural numbers isn't a pre-existing infinite set, but a process of constructing numbers one by one, always extending the sequence. This view leads to a radical shift in how we think about infinity. In classical mathematics, infinity is treated as a completed abstract entity. Intuitionism rejects this, however. Instead, infinity is seen as a potential, something that can always be extended but is never fully realized. You don't assume numbers exist, you construct them. For example, the number 100 exists not as an independently fixed entity, but as a result of constructing each step in the sequence from 1 through 99. The process itself is what gives the number meaning, rather than assuming it is pre-existing. Infinity, then, is not something you can grasp all at once. It's like running a program that keeps generating numbers without end. You'll never get to the end of infinity because it doesn't exist as a fixed totality. This constructive mindset also challenges fundamental principles of classical logic, like the law of the excluded middle. Classical logic says that any statement P must either be true or false, even if we don't know which. Symbolically, it is written as P or not P. Intuitionism, however, only accepts a statement as true if we can prove it, and as false if we can prove its negation. Without a proof, the statement remains undecided. For example, the claim there is life on other planets can't be classified as true or false until we have concrete evidence one way or the other, regardless of how many probabilistic equations one comes up with. Similarly, mathematical conjectures like the Riemann hypothesis remain in a state of limbo without proof or disproof. So just as Intuitionism treats the number 100 as existing only because we can construct it by extending the sequence from 1 to 99 or by using some other sequence, Intuitionism does not accept P or not P without a constructive proof of one side or the other. We cannot assume that either exists. We have to construct it. If you cannot construct a proof of P, you cannot claim P is true. And if you cannot construct a proof of not P, the negation of P, you cannot claim not P is true either. Hence, there are situations where neither P nor not P can be proven true. For Brouwer, this means the law of the excluded middle fails. So how would one show not P? In intuitionistic logic, you must first assume that P is true and then derive a contradiction or something absurd from that assumption. This process explicitly demonstrates that not P is true, as assuming P leads to an impossible outcome. So by proving something absurd when assuming P, we have effectively proven not P. This is known as proof of negation. In contrast, in classical mathematics or logic, one would likely use proof by contradiction. You assume not P, the negation of P, and derive a contradiction. Since the assumption of not P leads to an inconsistency, classical logic concludes that P must be true. The key difference is that in intuitionistic logic, to prove not P, you must explicitly construct a contradiction by assuming P, whereas in classical logic, you can conclude P simply by deriving a contradiction from not P, without needing to construct P directly. Thus, intuitionistic logic requires a more constructive approach to negation, while classical logic allows a non-constructive reasoning through contradiction. Proof of negation and proof by contradiction are essentially equivalent in classical logic, but this is not so in intuitionistic logic. There's a subtle difference. Through Brouwer's first act, intuitionism not only redefines natural numbers, but also reshapes how we reason about them, challenging assumptions about infinity and logical principles. But what about the continuum, the real numbers? To answer that, Brouwer introduced his second act of intuitionism. In Brouwer's second act, the leap from natural numbers to real numbers introduces the idea of choice sequences. Unlike the classical view, where the real number line is treated as a static, complete entity with every point predefined, Brouwer saw the continuum as a dynamic, ever-unfolding process. Real numbers aren't fixed objects, but are built step by step through choice sequences. Sequences that are infinite, not because they are already completed, but because they can, in theory, keep going indefinitely. Think of it like writing out the digits of pi as a process. You start with 3, then add 1 to make 3.1, then 4 for 3.14, and so on. Each digit is added one at a time, and the sequence grows with each step. Now, say you decide to mix things up. After writing 3.14159, you throw in a random 7 instead of 2, which would be the next number in pi sequence, and thereby making it 3.141597. At that point, you could go back to following the digits of pi or make up a new pattern entirely. The key is that the sequence unfolds over time, and the future digits don't exist until they're chosen. There's no predefined, finished version of the sequence. It's created in the moment. Some choice sequences are lawlike, following a strict rule or algorithm, like listing the prime numbers, pi, or the digits of Euler's number. Others are lawless, where each step is determined freely, like flipping a coin to decide the next number. A sequence could even start lawlike and then switch to lawless, or vice versa, like we did in our example of pi, where we threw in a random 7, thereby creating a new number and not pi in fact. The only thing we can ever know about a lawless sequence is the portion that's been created so far. The future remains open-ended. So for Brouwer, every real number is a choice sequence. All of them. Pi, 3, 1,500, -9, 1/4, etc. All of them are constructed freely with our mind using this notion of a choice sequence. This makes the intuitionistic continuum fundamentally different from its classical counterpart. It's less like a fixed static line and more like a piece of improvised music where each note depends on the last and the song evolves as it's played. The key point is that we can't predict what the next digit in the sequence will be until the exact moment it's chosen. There is nothing about the definition of a real number that says its digits must follow a strict rule or algorithm, and you can't peek into the future of the process to see how it will all unfold. For an intuitionist, mathematical reality is tied to the flow of time and our mind. Once a digit is chosen, that's it. It's locked in. You can't undo it without creating an entirely different real number. But until the next digit is chosen, its value and the values of all the ones that follow remains completely open to different possibilities. As can be seen, intuitionism, with its embrace of choice sequences and its rejection of the law of the excluded middle, brought about a new approach to mathematics and logic, one where mathematical truths are created through constructive processes, as opposed to relying on abstractions. But not everyone embraced this shift, and one notable critic was the mathematician David Hilbert. His opposition eventually sparked the famous Brouwer-Hilbert controversy. The conflict between Brouwer and Hilbert began with Hilbert's 1888 proof of the Hilbert basis theorem, which Brouwer rejected because of Hilbert's use of the law of the excluded middle. Hilbert famously responded, "Taking the principle of the excluded middle from the mathematician is the same as prohibiting the boxer the use of his fists." In the end, intuitionism encourages us to view mathematics in a fresh way, as a dynamic process unfolding over time, influenced by human thought and choice. It challenges the fixed nature of classical mathematics, offering a philosophy that focuses not just on understanding, but on creation, on construction. Whether you find this perspective freeing or confusing or whatever, intuitionism highlights that mathematics is more than just a mere set of rules. It is a deeply human pursuit, as complex and evolving as time itself.